Hello?
Yes, it's me, Hugo.
Hugo, okay. How are you?
I'm good, and you, my friend?
Where are you from?
I am from Brazil too.
Okay. Okay.
Yes. Can you
Are
hear
you
me?
ready?
Yes, I'm ready. Um,
Okay.
how can I show my screen here?
Can you share or not?
Um, my screen to show my presentation. How can I do that? I'm looking for this.
In share
Plus.
screen.
Yeah, where is it?
And down.
Yep. Okay. Right here. I'm sorry.
No problem.
Are you seeing my screen?
Yes, I see that.
Yeah. Let's.
Okay. So Hugo Valadares is okay?
Yes, it's me.
Hugo Valadares is present the title, the paper with the title Performance Comparison of Machine Learning Model for Streamflow Forecasting. Are you
Yeah,
ready, Hugo?
I am ready.
Okay,
Um,
are you?
okay. So, good afternoon for everyone. My name is Hugo Valadares Siqueira. I am from Federal University of Technology in Brazil. Okay, this work was developed together with José Fernando Toledo, who is a PhD candidate at Federal University of ABC. Professor Patricia is his advisor, and the Dr. Rodrigo Sacchi is a colleague who worked with us, and he is from the Chamber of Commercializing Electricity in Brazil. Today, we are going to talk about the performance comparison of machine learning methods for streamflow forecasting. Okay, so our agenda was divided in introduction, a brief theoretical reference, some materials and methods, the results, and a discussion about these results and a conclusion. Okay, in here I show you the hydroelectric power plant from Embarcação, one of the plants we use the data to perform the predictions. So streamflow forecasts is a very important kind of time series for countries like Brazil, because we are very dependent on the stream flows on the water to generate electric power. Okay, so all the planning process and the operational planning process of the plants need needs actually the accurate stream flow prediction. Okay, and in this sense, much has been developed in the last years regarding stream flow forecasting. Of course, linear models from the Box and Jenkins family, especially, but in recent years, I would say the last 15 or 20 years, machine learning techniques, especially artificial neural networks, stood out in this sense. Okay, in this very investigation, José Fernando started to use some machine learning techniques like extreme learning machines, which are a kind of neural network. Okay, support vector regression and kernel read regression. Okay, why he used this kind of technique? Mainly because these models is not so require not so much computational effort to be trained like the traditional neural networks. Okay, and also we create a time series with the error of the predictions to evaluate the performance of these three models. So what are the extreme learning machine? These techniques were proposed by Huang in 2004. Okay, as all artificial neural network, it is a nonlinear methodology which means these techniques or these models can map some sets of inputs and outputs in a nonlinear way. Okay, this is a feed-forward architecture, very, very similar to the traditional multi-layer perceptron, okay? But with a very important difference. The hidden layer present fixed parameters, which means that we generate the weights of the hidden layer, and these weights is not they will be not changed along the training process, okay? And the output is just a linear combiner. In this case, we use the pseudo inversion of Moore-Penrose. Okay, of course, this is a neural network, but it presents a very fast convergence, and they present the extreme learning machines present generalization capabilities like almost all neural networks. This is the architecture we are presenting. This is the inputs, the hidden layers with weights, and of course we will not train these weights, and the output is just a linear combiner, and you use the famous Moore-Penrose inverse operation to train or to calculate the weights of the output layer. Okay, we also, in this investigation, use the support vector regression and the kernel ridge regression. These two methodologies are indeed similar in many aspects. They are, of course, adaptations of the traditional SVM classifier, okay, for regression and prediction. And the main difference between SVR and KRR is the loss function. While the KRR uses a square error loss, the SVR uses the epsilon insensitive loss. Both optimize a convex or a unimodal problem during the training phase. And it's very, very common to use the famous kernel trick or to perform nonlinear mapping. And in both cases, we also can have outputs with continuous, we have continuous outputs when training the models, okay? In the SVR, we are looking for the best values, the best value of the series that present the maximum value of epsilon from the expected value, okay? And the values we are during the regression inside this region formed by the epsilon, it's not calculated. In the KRR, the constant omega is not calculated, is calculated indeed in our work using the cross-validation. And it's a kind of imposed penalty. In this sense, we use as parameters of these three models. These values we are presenting here, of course, it is in the paper, and we defined these values based on previous tests or empirical tests. Okay, and we have in here 6 scenarios. We have actually 1, 2, 3, 4, 5, 6, 7, 8 plants, or 8 time series of a streamflow series from these plants, okay, Funil, Boa Esperança, Coroa, Una, and so on, okay. And we use 6 different scenarios in which we consider the ENSO or the El Niño Southern Oscillation in some cases. In the other cases, we use climatic indexes like intertropical convergence zone or South Atlantic convergence zone, which can influence the response of the predictors, okay? And we made some kind of miscellaneous in here, combining the presence or not of this stuff in here. And in the scenario number 4, we also consider the precipitation or the prediction of the precipitation for the next days, okay? And in here, I present for you where is located each hydroelectric plant. northeast, north, middle east, and southwest. And this number in here is the number the electric sector in Brazil gave to each hydroelectric plant. As you know, we have more than these 8 in Brazil. Just to show to you the ITCZ I mentioned here, Intertropical Convergence Zone, influences the rainfall in this area in here, while the SACZ influences this specific area. So we are investigating if the use of these variables in here can change or can modify the response of the models. So we performed 12-step ahead predictions, okay, to investigate the long-term prediction of these models. In some scenarios, we did not consider the influence of ENSO. Okay, in this case, the forecast period is from January to December, and when we are using the ENSO as input, we consider as a forecast period August to July. Okay, so we performed the predictions and then we applied 2 statistical tests, the Kruskal-Wallis and the Levin test, with 5% of confidence. Okay, for our surprise, but it's not a so great surprise. For each scenario I mentioned before, the values found for the p-value in here is too high, much above 0.05 or 5%. Which means there is no significant difference between the response of these models, okay? But the hypothesis is, the question is, if I would like to implement some of these models, which one I should choose? That is the question, since we don't have a difference among the p-values in here, p-values in here. So we created also a time series of the errors. Okay, so we predict the models and then we calculate the residuals, and these residuals gave to us a time series. And then, considering that 6 scenarios I mentioned before, I investigate in which case I have the lowest average. And here, as we can see, is a little miscellaneous, but the key KRR, most of the cases was the winner. Okay. In these 2 tables, I present to you the average of the error. Okay, in this both case, in this case of the 6 scenarios in here. There is an equivalence, as I mentioned before, regarding the statistical tests. However, if I observe just the absolute value, most cases the KRR present the lowest average. Okay, and also when I compare the total results of the models and just observe which one present the smallest error, I will see that the most part of the best results is favorable to the KRR, which present the smallest error in the 3 scenarios and in the 3 regions. Okay. So here I present to you just an example for station 2177. Let's see which one is 77. It's here. Okay, Coroa Una. Opa, Coroa Una. Okay, so I took the test set of this case, and as I can see, this is the case without just univariate time series forecasting. In here, I am considering, for example, the precipitation. Okay, and you can see here the response is quite similar, but in here there is a great difference. Great, I'm not sure it's great, but it's graphically possible to see the difference between the responses of our models. Okay, SVR, LM, and KRR. In this sense, As conclusion, we use, as I mentioned, 3 machine learning methods and 6 test scenarios. Okay. When I insert the climate indicators, I create a more complex scenario. Okay, because I am inserting exogenous variables, or in this case, I have a multivariate time series forecasting. Okay, and also these variables may help me to create a better forecasting using that models. As I saw, as I showed to you, the statistical test indicated that there is no difference between the error, considering the times I ran these algorithms. But the KRR produced the lowest average error in the scenarios we presented. Okay, and SVR and LAM performed equally well, almost the same. Especially in scenario 4, when I use rainfall, we observed that the performance of the KRR was increased. So this is our presentation. I let to you the contact of Professor Patricia LACCI, and I am available if you have some questions, and thank you for your time.
Okay, thank you very much, Hugo. Excellent and presentation. Congratulations. Okay.
Thank you.
I have some question about why do you think that KRR is in your result a little bit better than SVR and ELM?
This is a tricky question. Many times I heard something like that when I was in some presentation, because in my experience in time series forecasting the last 15 years, what I observe actually is that the performance of the method is like depending on the set of the data, depending on the data set. Some works I have done in my career, I observed that most part of the good results did not belong to a linear model, for example, or even to a SVR or something like that. Maybe this is, I'm not sure, I cannot say that because as I said, if I change the series, I have different results. But in my opinion, depending on the series, let me show you something here. Okay, many times we are using SVR or KRR. The cost function we are optimizing many cases is unimodal, so I can have a better approximation of the cost function I am trying to adjust the parameters. But if I apply, for example, an autoregressive model, in the same case, I also have the an unimodal cost function to be optimized, but not necessarily I will find a best result. So, my friend, I should, not I, but a further investigation on how the series behave according to the linear dependence, for example, or something like this, must be done to interpret how, or the reasons why just this method could be the best. And look, KRR is quite similar to SVR, and
Yep.
KRR was better than the both. Okay.
Okay, thank you. And another question, in the 6 scenarios that you use, you have the same configurations? Or is one model for all, or you train individually each
So
one?
no, yeah, you use the same configuration. Of course, it could be changed depending on on the scenario. But in this case, we try to use the same variation for all. So when we are applying the empirical previous test, we try the same variation for all. It's because the range of the possibilities is too high. If I try to change all of them, I would took a lot of time. But I agree with you. The best case is to change the parameters for each case.
Okay. One question is in you have tried another configuration, another type of machine learning method like LSTM. By example, they use a memory from especially for time series, something like that.
José Fernando is doing this very time. He is a
Okay.
PhD candidate, okay? So
Okay.
at this time, after we elaborate this paper, he's doing the next steps, which is
Okay.
trying other machine learning techniques or even combining models. I will present another work in this very section, but he's trying, for example, ensembles or LESTM or MLP, RBF, and there is a universe of possibilities in here.
Yeah, but when you work with time series, the idea is to you have some memories because you can analyze some trends, something like that.
Sure, sure, sure.
Includes in but okay, it's another topic. Okay, bye. Thank you very much, Hugo. Nice
I
work, very
appreciate,
nice work.
Professor. Thank you.
Okay. Okay, we have the next paper is from Dennis or Fernando.
Yes. Hello, everyone.
You are Eric.
Yeah, I'm Eric's.
Okay.
Let me share my screen
How
here.
are you, Eric?
I'm okay, and you?
Thank you. Thank you. You are from Brazil too?
Yeah, I'm from Brazil also.
Okay, thank you. Okay, now Eric da Silva present the e-read model with error correction for wine speed forecasting. Okay, nice topic. Ready, Eric?
Presentation. Ready? It's from the before presentation.
Okay, we see that
It's the screen of Hugo. I can't share my screen here because I needed that
I
the
see your
other
screen.
user.
Eric, I see
No,
your
it's
screen.
not my screen. It's not my screen. It's from Hugo.
Okay.
Yeah.
Sorry.
So let me share here. Just a second.
I'm sorry, Eric.
No problem. No problem.
Okay, that is the title of your paper. Okay, I'm sorry. Now Eric da Silva present us the paper automatic future engineering using self-organized maps. Okay, Eric, are you okay? Eric?
Are you hearing now?
Yes, I can hear you. Are you okay now?
Okay. Yeah, I'm okay now.
Okay, go on.
So let's start. Hello, everyone. I am Marix. I'm going to talk about the automatic feature engineering using self-organized maps. This was work did by me, Erix, and Dennis from the University of Munster, and for Fernando Buarque de Lima Neto from the University of Pernambuco, together with me. So let's start. So feature engineering is the process of generating new relevant features from the original features that you have in a dataset. This new relevant features produces a new perspective of the feature space, where in this feature space, the process of data separation is more easily to be executed. So to exemplify that, here we have a data set of products that in this case we have code that has as features the price and the weight. And for example, a data scientist can analyze this data set and identify that the combination between the price and the weight of the product can bring a new relevant information about the data that is being analyzed. And it starts the process of classification, for example, that is the main objective of this work to be executed more appropriately. So the process of feature engineering is not an easy task at all. It demands an in-depth knowledge about the domain, It demands a strong relationship between the data scientist and the businessman, and it demands a lot of time and money. So to alleviate that, a couple of techniques called automatic feature engineering uh, proposes to use, instead of the data scientist to analyze the data set, use of the machine learning technique to do this job, and also generate new relevant features to our final machine learning model, in this case for classification. So talking a little bit about the works related with automatic feature engineering, they has focus on work with transformation functions. So what are transformation functions? Are simple math functions such as square root that transform a feature or a set of features of one domain to another domain. And this work, this transformation, this works of automatic feature engineering tries to find the best transformation function, tries to find the best sequence of transformations, find the best features, select the best features to be transformed by specific transformation functions at all. Our approach that we proposed here, the self-organizing automatic feature engineering, it works a little bit different from that approach. So our approach focuses on the organization of the features that you have in the dataset. It's focused on the patterns, the similarities, the differences between each feature that you have in this space. So to do this process of generating new features based on the patterns that we have in the dataset, we chose to use it unsupervised machine learning technique called self-organizing map. The self-organizing map is a neural network approach where it produces a map that brings a reduced dimensionality of the datasets that you have been analyzing in this time. So this map brings a lot of information about the similarities and the difference of the features that you have. For example, how this map organizes the data after the training. When I have a feature that have a set of features that of data that have a lot of similarity with each one, it's placed in a position closest or in the neighborhood of this set. But when I have another set that has very much difference between each feature that we have, they are placed in a different position far from that one. So this perspective proposes a topological map that brings a lot of information based on the organization and the difference and similarities of the dataset that you are investigating. So how the self-organized automatic feature engineering works. So this initial approach that we bring here, it's very simple. We have an original dataset with all the data. So we take a random sample of this dataset to and use it to train our self-organized map. And we generate our map with the weights of the network that produces the map at all. After we finish this training, we use the weights of the self-organized maps and we pass through them we propagate the information that we have in the original dataset that we have, and we multiply each value of the feature for its respective weights for each output that we have about the self-organized map. So we send the produced features and the original features that we already have in our dataset together to our final classification model. In this case, we use the random forest classifier. So for the experiments that we executed, we defined some simple configurations about the self-organized maps. We choose to use the dimensions 5 by 5 of this map, where it will produce 25 new features. and with some configurations, simple configurations, well-known configurations of the self-organizing maps. For the data sets that we have, we select some data sets that are very used for a lot of machine learning approach, and also is very used for automatic feature engineering approach that we found on researchers. These data sets are Hill Valley, Ionosphere, Sonar, Spanbase, et al. And for classification models, we use the library provided in Python that is scikit-learn. We use the models KNN, Random Forest, Decision Tree, and the MLP. We use the default configuration that this library provided to us. And to evaluate the quality of the results that we obtained, we use the F1 score. That is a metric that is well used also for automatic feature engineering approaches. So for the first step of the experiments that we executed, we can see here in these box plots, the two box plots on left are the box plots comparing the not using or using the self-organized automatic feature engineering. And the two on right are the same thing, but here we use a simple technique of feature selection. The behavior that we can observe in these experiments is when we use the self-organized automatic feature engineering, the new perspectives that we produce generates a high variation of the results that without using the self-organized automatic feature engineering. So the maximum values after 30 interactions that we execute each model with each combination of the dataset, in this case, we are evaluating the Hill Valley and the decision tree, we can see that the maximum value that we can find executing 30 times the process of training uh, can be observed that this maximum value increases, but the minimum value also is lower than the without using. We can see that in the feature selection approach also, but it's a little bit more conservative. It's a little bit more controlled. So I bring here also another dataset combined with another technique, in this case with megawatt one with random forest. And you can see that without feature selection, the same behavior of the expansion of the variation is still happening. But in this dataset, with feature selection, we can see that the results don't change so much. Here we have a particular case for the span-based dataset that is dataset very sparse with many zeros, and we use in this case the KNN technique. So we can see that in this particular case, we don't have so much any difference between using or not the self-organized automatic feature engineering. But we can see that with feature selection, our approach, because of the patterns of the similarities that are provided based on distance, it brings interesting results that amplifies the quality of the results significantly of the results obtained with this approach, in this case, the KNN. So we also did a simple comparison among the self-organizing map dimensions, where we define different sizes and see how the behavior happens. So in this case, you can see that with 5 per 5, we have a low case of variation. And you can see that with 10 per 10, we have a highest variation. And with the maximum value of the sample that we have is pretty high than the other example that we see. So it's we can observe that we can see that the selection of the correct dimension can improve significantly the process of the technique that we propose. So we produced a novel technique, a novel perspective to generate new features using unsupervised learning technique based on the characteristics of the learning of the structural pattern that you have from the feature space. So the main advantage I better say the main difference between the self-organized automatic feature engineering to other techniques is that we don't need a predefined transformation functions at all. And the limitations that we have is that the results that you obtain has a high variation. So we have also to define the best dimensions, that this dimension affects significantly the quality that we have. And in future works, we are working to set the best hyperparameters for this technique. So that's it. Thank you.
Okay, thank you very much, Eric. Very good presentation.
Thank you.
Can you show the slide 14, please?
14, just a second.
Okay, when you
14,
have,
that's it.
no, it's okay.
Okay.
When you say about the dimension affect quality, what mean about that?
Yeah, I will put in another slide. Here, when we have, it, for example, 10 per 10 dimensions, we can see that the maximum value that we obtained for this dataset, the Unistore dataset, is pretty high than the other dimensions that we have. So it's very interesting, but we can see that also we have the minimum value also has a minimum value. So when we can improve the results, we best can define the best dimension that better represents my data set. It was clear?
Yes, and another similar question. Can you reduce the dimension like an extra step? By
If I can
example,
reduce
using,
the dimension,
yes.
yeah, I can reduce the dimensionality, but this work that we use it was has the objective of bringing more dimensionalities. We don't analyze it yet, but we can use also the dimensions provided by the self-organized maps. It can be a future work, not for do only a feature engineering approach, but also a feature extraction. It can be very interesting also.
Okay, we have a question from Paulo. I think it's similar. How do the feature obtained with self-organizing map compare with more typical method like a PCA? How do you calibrate the? It's two questions. This is the first one. How do
Yeah,
feature obtained with self-organizing map compare with more typical method like PCA?
the self-organized map, it works from has a score to central operators. For example, we have the operator of learning, where we have the cognition of the process, where initially our process search more in the feature space. We have a higher capacity of exploration through the feature space. And when the time when I have more interaction, it specifies on the in a specific region. It turns more material in the decorrer. Durante o process, I can generate more. I have more specific. I can work more with the exploitation in my feature space. And the other operator that we have is the question of the distance of the similarity that we have of the data set. So in this case, we use the Gaussian function that how close of my data is from another, from the neuron that represents his position, it has more effect through this neuron at all. But how much far it has a less impact on this neuron. I think that is how the self-organizing map works. And how I can calibrate this sum, it's an interesting question. And we are working on that. We have some results that we use the evolutionary strategy. It will be in future works to improve the results based on the feedbacks that we have about the classification that we are realizing based on the results. So some hyperparameters such as the sample size, the size of the self-organizing map, And we have another operator also in currently that we will not cover for this research in this moment, but it will be published in future works. Are have a lot of hyperparameters that are have been automatically defined by the evolutionary strategy. So this initial research is just for more exploration how the behavior of the self-organized maps impacts in the generation of the new features that you have.
Okay, thank you, Eric. Last question is from Christian Aravena. He asked if you
Okay.
compare with other metrics.
Not yet with other metrics, not yet, because I produced another work that will be published in another conference that I compare with other automatic feature engineering approach, and we received very interesting results that are very comparable with other approaches. But overall, the work that we found are focused on F1 score to evaluate. So we don't evaluate other metrics for this in this case.
Okay. Okay. Thank you very much, Eric. Thank you for your answer and congratulations.
Thank you. Yeah.
Okay. Thank you. We have the next presentation. Presentation is from Tatiana, Lucas, Eric.
It's me again, Professor. Hugo.
Hugo, hi, how are you again?
I'm good, my friend.
Okay.
Mi amigo.
Yes. Eric, Eric, Hugo need to share. Thank you.
That was my time, sorry.
Okay.
Okay.
Are you seeing my presentation
Yes.
here?
Yes. Yes. I can see.
Interesting.
Okay.
I can't see my screen in here, but I can see in parallel here. No problem.
No, I see your slide. It's okay.
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 Nice. Please, Eric's, just regarding the presentation from Eric's, please send a hug from my great colleague and friend, Fernando Buarque.
Do you know Eric?
I don't know Eric, but I know Professor Fernando.
And
He's
we
a
all
great
know,
friend from Pernambuco.
all know Professor Fernando. He's very famous.
Everyone knows. We're gonna meet him tonight, yeah?
Really?
There is a meeting tonight, and there we can talk with him a little bit.
But virtual meeting
nice.
or not?
I intend to participate.
But virtual or in real?
No, just for in here virtually.
Okay.
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 So,
okay, let's start. Okay.
Please.
Now Hugo again
Yep.
sent us a paper with the title "Hybrid Model with Error Correction for Wine Speed Forecasting." Okay. Do you like this topic? I understand.
Yeah, a lot. So thank you, Professor Fernando, once again.
Okay, Hugo. You can start now.
Okay, thank you very much. As Professor Fernando said, a hybrid model with error correction for wind speed forecasting. This work was developed by Tatiana, who is a master's candidate, which I advise. Lucas, Erickson, Marcela, Professor Maura, and Professor Paulo from Pernambuco too, as Eric's, and me, the advisor, Professor Hugo Siqueira. We are at Federal University of Technology, and Professor Paulo is from Federal University of Pernambuco, both in Brazil. Our agenda today, we're gonna discuss briefly an introduction. We're gonna discuss about the single forecasting models, linear and nonlinear ones, okay? Our proposal for this investigation and the discussion about the performance and the error metrics and the experiments, and also to finalize a conclusion about this work. So in the previous presentation, we were discussing about stream flow forecasting, which means we had water. We are predicting how much water we're gonna have to generate electric power from hydroelectric plants. But As we know, is widely known that in the last times, in the last 10 years, maybe, the wind energy stood out. Okay, many money and the resources is applied to invest in wind power generation in the world. Okay, in 2020, Brazil totaled almost $900 million in investments of this kind of source, the second position in the world, just behind the United States. And the interesting thing to Brazil is that the northeast region of this country has a great potential, a great wind potential. Okay, and to perform the series regarding the wind speed, for example, we can use physical models, statistical models, or even artificial intelligence models. Uh, uh, Many of these models are in the literature. Okay, but another possibility which is gained prominence in the last years is the combination of different models to increase the capability of the models to predict or to perform the predictions. In this sense, this investigation will discuss a hybrid system based on error correction to perform wind speed forecasting, considering both linear models and artificial neural networks. Okay. So, as I mentioned, the Brazilian Northwest, in here, we have the Atlantic Ocean. Okay. And here, in red, mainly in red and yellow, one can see how the velocities are strong comparing the rest of the country. Of course, here in green is the rainforest, so we don't have many wind power in here. But here, close to the Atlantic Ocean, the speed of the winds and the concentration of the winds are strong enough to generate uh, um, uh, aeolic energy. Okay. And then most of the wind farms in Brazil are located in northeast. And to predict the wind power, or actually the time series regarding the wind velocity or wind speed, we can use, for example, the famous ARIMA model, or autoregressive and moving average model, ARMA in this case, because we are not using the eye of the ARIMA. And then how can I proceed the use of this model? Actually, I combine the previous values to predict xt, and x is a value in the future. I can combine, for example, the past values t minus I, which I is a value from 1 to p, or the order of the R model, or the autoregressive component. And here we have the moving average component, which combines weighting with this weight theta, the white noise epsilon. Okay. But as it's common and in the literature, we use as the white noise the error of the last temporal prediction provided by the model in the time immediately before the prediction I am making. Okay. Also, we tested the famous multi-layer perceptron. As everyone knows, this is a feed-forward architecture. Okay, in here I present to you the expliciting the middle or the hidden neuron. Okay, this is the weights. This is the junction sum, the junction part, the activation function, and here, considering just one output, I am presenting to you the output neuron. Okay, and here, most of the time we use the as activation function the linear one. Okay, in this case, despite we have a lot of possibilities to train the MLP, we are using the traditional backpropagation algorithm to adjust the weights of the multi-layer perceptron. Okay, But note, as when we know, this is a iterative process. So I do many executions in a loop, okay, to adjust this weights. I mentioned 10 minutes ago, I discussed about the extreme learning machine, so I will not say everything again, but the most important thing to remember is that the hidden layer or the weights of the hidden layer is not trained. So the adjusting time of the extreme learning machine compared to the MLP is too small, okay? Indeed, both architectures is quite similar. I can use the same neuron in here, exactly the same. But as I mentioned before, I just train the weights of the output layer, which can be done using the Moore-Penrose inverse operation, which present a closed loop form, okay? Closed form solution, I'm sorry. But in this case, we are addressing the possibility based on the methodology proposed by Zhang et al. Zhang said that we can use a time series forecasting, can address the time series forecasting by this approach he proposed in 2003. In this case, we can we perform the predictions of the model of the series, okay, and using an ARMA model or an autoregressive model or any linear model we want, but mainly the literature present the ARMA model, okay? After the predictions of the ARMA model, the residuals or the error of each sample forms a new time series based on the error, which means that I have the prediction of the model using the linear approach, and then I will use the time series formed by the error, and I will predict this time series considering the error by an artificial neural network, for example, or each nonlinear model I want. So the final prediction will be the composition of the linear model, of the linear response, and the error provided by the artificial neural network. Okay? Why you can do that? The hypothesis that Zhang, I'm sorry, presented is that if I use the linear approach to predict the series, the residual must be nonlinear because the linear pattern was modeled by the linear model. Okay, so this is the hypothesis Zhang addressed in the literature. In this sense, as I mentioned, we use two databases from Northwest, one located in Natal, in the state of Rio Grande do Norte, and another one in Petrolina, located in the state of Pernambuco. Okay, this is the number of samples in each case, the mean and the standard deviation of each case. Note that Natal database present a higher mean and a higher standard deviation. Okay. Initially, we applied the augmented Dick-Furler test, and we observed that the series were stationary. Okay. Then we applied the ARMA model. Okay, the order were defined by the methodology proposed by Hindman and Kandalkar, and the LAM and MLP, the inputs were defined previously using the wrapper methodology. As I mentioned, the MLP was trained by the backpropagation, and the ELM trained using the Moore-Penrose inverse operation. Okay. In the experimental steps, we addressed the one step ahead forecasting, okay, using the MIE and MSE errors, okay, mean absolute error and mean squared error, okay, and we applied the linear models, the single models I presented before, the ARMA, ALM, and MLP, and then a combination of them regarding the idea from Zhang, okay. The results we achieved actually showed that the the proposal composed by ARMA plus MLP to predict the error series, we have most of the best results considering both metrics. For Petrolina, this model achieved the best results. And for Natal, the smallest MSE is achieved by ELM, but the MIE is achieved by our combination. Okay. For our surprise, this is a little unexpected. As I mentioned, Professor, in the last presentation, look, the MLP, despite its nonlinear methodology, the ARMA was a little bit better. So for this time series specifically, the MLP did not work well in Natal, I mean. Okay, but the combination and the ELM achieved a good value from MSE in this case. Here I present to you the box plot of both cases, Natal and Petrolina, and as one can see, the application of the combination led to a smallest dispersion than the single models, especially the case with the ARMA with MMLP, which is the general best. Okay, so that combination in this investigation showed be better in both cases to achieve the smallest error, and also the prediction is more certainty. Okay, which means we found almost all times the same values in here, which is very good for us who like to work with time series forecasting. And here I present to you the best response we found. Consider the ARMA MLP combination, the actual value in black in both cases, and the red is the prediction provided by our model. Okay. So as conclusion, I can say to you that this time series is a little complicated. It's very volatile, and it's a challenge task to perform forecasting using these databases. Okay, and in this case, the hybrid systems can be good candidates to solve the task. In Natal, we observed that the LM achieved the best MSE, but for all other scenarios and for both metrics, the combination of ARMA with MLP led to the smallest errors. Okay. As future works, we are going to discuss to apply an ensemble, especially in the second stage of the hybrid model. We have a kind of we are putting in a line, okay, the models. We can do this, and we discussed it before. We can use LESTM because LESTM present memory, and also other kind of unorganized machines like equistate networks, which is a recurrent neural network and also present memory, but different from the LSTM. The ESN is light, very light to implement, to train like the ELM. Okay. Here some important references we use in this investigation, and I thank the audience for to hear us here. Thank you very much, Professor Fernando.
Okay, thank you very much, Hugo. Is Hugo or Hugo?
Hugo. Hugo is okay. In English.
Okay, but the name is from the is like you want.
Yeah, but if I say Hugo in the United States, they never understand my name starts with an H.
Okay.
But it doesn't matter. Hugo, it's good.
Okay, Hugo. Excellent presentation. Very good.
Thank you very much.
I have some question. Can you
Please.
show me the slide when you show the hybrid system, the model of hybrid system based on error?
Here.
Okay, that one. Finally, the combination is there is some weight from the output from ARMA model and artificial neural network in the combination step?
No, I just sim their responses. There is no weight here.
No weight. Okay,
That's the original idea from Zhang. As I mentioned, he thought, if I use a linear model to predict the original series, the error or the time series regarding the residuals must be nonlinear. But he did not present any kind of, in this original version, of course, he did not present any kind of weight in here for both components of the output response.
Okay, for the trained artificial neural network, in this case, and MLP, you use previous data, or it's merged?
Yeah, actually, I use the error series. I don't use the original data. I don't use wind speed. I just use error.
Okay, but the error is with the time series before the testing period, or not?
I'm sorry, could you repeat?
The data for training.
Okay.
Is from a period of time?
I use the same time length in here. If I am predicting, for example, t equals 10, okay? I use the predict for t equals 10 and the error from t equals 10 in the training. In the test, of course, I can adjust because I use this just the next time. You're right, because I don't have the next time, so I can use just the time before.
Okay, and can you show me the result, please?
The results here.
That one. Okay, the MLP that you have the 45 is this mean square error. It's a lot.
It's a lot. It's surprisingly me too. Yeah, as I mentioned before, it's not expected.
Yes. But when you merge with ARMA, it's the same configuration of MLP.
No, here I train again. It's not the same configuration because in here I'm going to train the errors, the error series. Not the series, the original series.
This is the model. This is the model. Okay, similar to ARMA, but in MLP. Yeah, I understand. Okay. And in extreme and LIM, you have better results.
Yeah, extreme learning machines. Yeah.
Yes. Can you show me the time period, please?
Here?
No, before.
Time period?
No, sorry. The next one, please. Not okay. Okay. Yep. This okay. Okay. It's very good. We have some question. Another question from Paulo. Who is it? The residuals could still be linear if the order of the ARMA model is insufficient. What is the order of ARMA in this case?
I can show you, Pablo. Can you see my screen?
Yes, I can see.
This is the original paper. I didn't put this information, but we have in here. Okay, here. The order of the ARMA is 1 and 2, and we extend this 1 and 2 order to the combinations, of course. And I agree with you. If I use an insufficient order to ARMA, maybe the residual could present or may present still present it's better a linear part, and I totally agree with you. Actually, in this case, we trained the ARMA with the traditional maximum likelihood estimator, but we can apply, for example, to adjust the ARMA model, we can use the genetic algorithm PSO. In most cases, we can achieve better results than the traditional maximum likelihood estimator. But I agree with you, Pablo. But in this case, we use the indications provided by Professor Hindman to use this approach in here. Okay.
Okay. Thank you very much, Hugo.
Thank you again, Professor. Thank you very much. Thanks.
See you, my friend. Okay, we have the last presentation now from Bruno. Bruno?
Hello? Yes?
Hello, Bruno. How are you?
We're fine, we're fine. Just fine.
See your,
Second working.
can you share
Let me see.
your slide, please?
Here, let me see if I can share screen. It's not letting me yet. There. Can everyone see, right?
Yes, I can see. Are you ready?
Perfect, I'm ready.
Okay, you can start now, Bruno.
Perfect. Welcome to everyone. My name is Bruno Gutierrez with Mireille Clemensal Diaz from the University of La Frontera. We did a systematic mapping of smart farming and image recognition in agriculture. Without further ado, let's start. First of all, I'm going to talk about the problem that we started researching. We found out three main problems in agriculture, like today, especially in Chile. First of all, we have to talk about the world population. And since 2014, the world population is expected to grow to a whopping 9 billion, over 9 billion. This will mean another stress of food production and industrial production on different kinds of crops. We're talking not about all the crops for eating like corn or rice or potatoes. We're also talking about crops for industry process like rubber or cotton, similars. This will mean that the world needs more arable land. And right now we're kind of running out of arable land in the world. Secondly, we are having heavy effects of the climate crisis. Here in Chile, in the 6th region, 2 years ago, we had a really heavy drought that affected especially the agricultural and rural sector. And we can expect that as the climate crisis effects grow, this kind of climate and weather effects, what disaster will become more common. And thirdly, talking about plant disease sector in Chile, in the 9th region, we have a lot of rural farming. This means farmers that live far away, that don't have access to a cooperation or cooperation funds and resource. And so when they have a disease in the field, they can't really talk to an expert in order to find out what disease they have in their crops. Even more, if they talk to an expert, the expert will have to go to the field and see with his naked eye what kind of disease there might be, and maybe they can take the leave to a laboratory to do more research and tests. In those 2-3 days that might last, the disease is still spreading in the field. So we have to create something to leverage the problems. Our objective, here in this study mapping, was to identify different applications of machine learning and trends of learning, tools, extraction, data that's being used in order that we can create more efficient, smart farming and agriculture here in Chile, with a secondary emphasis on image recognition, because images and pictures are one of the easiest data acquisition that we can do right now with rural farmers. Between 60 to 70% they have access to smartphones, so we can use that. Our research questions, as we can see here, are mainly oriented in order, first of all, about the applications that we have, and later about specifically in image recognition with machine learning, what kind of image and tools are being used. So our research funnel, we started about searching of different keywords on agriculture and artificial intelligence, and IEEE and Explore. This had about 309 papers, which then we filtered down to 71.7 that we did the first big analysis, where we find out what kind of application was there and what kind of field. Later, we subsampled this in order to focus and narrow down on image recognition, which had 41 papers in our research. And we kind of found out there what kind of models, what kind of data, and what kind of applications were being done there. So, for analysis of this systematic mapping, first of all, in the use of machine learning and image recognition, we have to see that in general, in the field of agricultural smart farming, the yield prediction is being the main focus of the research, followed closely with water management and soil management. The whole task of smartly and optimally using the resources is of great importance as we will see, mainly because we are still talking about limited resource. A second important thing is that in machine learning and smart farming in general, we're seeing a large number of non-functional requirements papers. Like, for example, papers that are talking right now about how can we automate and find out what kind of sensors are having errors of lecture, or how can we talk about the ownership of the whole array of IoT in smart farming, or even more, how can we shorten the gap between rural farmers and smart farming, especially there have been a lot of investigation there in India and Brazil, if I recall correctly. On the other field, on image recognition, we are seeing a lot of geoprediction problems being addressed and solved, and especially disease detection and crop quality, that are problems that can be easily being done with pictures and with other kind of sensors. We are not seeing a lot of, for example, non-functional requirements or water management solutions in image recognition, almost nothing of soil management. I imagine because it's kind of harder to get soil data with pictures. Further ado, in the point of machine learning, can you see the graph here on the right? It's not covered, it's covered for me for the screen. Let me see here. There, can you see it here? On the y-axis, we have the types of image being taken, and in the x-axis, we have the kind of problem being addressed. In general, in the tools for image, as you can see, field images are the main image type of image being used, followed closely by satellite image. Satellite images were the most popular pre-2015, but later there has been more a boom of aerial images, especially drone images, that can be used almost across all fields. It's important to point out that most of these papers use photography images. As we can see, there's only one or two types of images that can be classified as photography, sensor image, multispectral image, while the rest is being taken with cameras that can be found on drones, UAVs, smartphones, and similar. Secondly, about the models being used, as we can see here, CNNs are kings. Here we can see again in the y-axis the kind of models being used in these researches, and in the x-axis on the left we can see the problems being addressed, and on the right we can see the image being used. Again, CNNs, they have been the most popular models being used, especially in field images and aerial images, while SVM sector vector machines are more as generalists. They are being used in a wider range of problems, almost all kinds of images. They are not being really limited to photography images. We can see also that the other types of models being used, such as section 3, random forest, rodent algorithms, are not as popular as SVMs and CNNs, at least for now. Here, another graph with the models and the years. We can see that between 2017 2018, there's been a bigger boom of not only CNNs, but also other kind of models that are being used. So maybe we will see during the following years more research about this. Running up the point of the systematic mapping, we then did experiment on how is disease detection being developed using this kind of algorithms. About the state of the art that we found out, we saw that the publications were mainly being developed using SVMs and DCNNs. Comparative studies show that SVMs they have a lower accuracy than the DCNNs. They also have a lower training cost and can be used with multiple data sources. They're not so limited to working with images. They can also be used as a discrimination classifier. They do not work as feature extractor, so that's why most new research is being done using DCNNs that will they have a more costly computational training cost. They also have a lot higher accuracy and results. Important to know that these two are not mutually exclusive. We are seeing researchers using something like a fast RCNN pipeline, fast region CNNs that use sector vector machines, super vector machines to find out the regional extraction after the model is being, after the picture is being passed to a DCNN model. So there can be a fusion of them in the training pipeline. However, in this paper, in this investigation, we focused on DCNNs, and especially then DCNNs in training in Plant Village. Plant Village is a data set that is this has become the baseline data set, in this disease detection in plants. It was developed by Hughes in 2015 and has been used in various DCNN applications. Here I'm pointing out two with Mohanty and Florentinos that each achieved over 99% accuracy using DCNN models. As we can see in the pictures, the dataset is mostly being composed of pictures of leaves, in both from the front and from the rear, with different kind of lightnings, but only focusing on the leaves. They do not present, for example, bark or tree. There are photographs taken in laboratory conditions. The training cycle we use is mostly regular training cycle with 80-20 speed validation, and we use it as an innovation, the techniques detailed by L. Smith on one-cycle policing and the use of learning rate test. Smith proposed in 2015 a training methodology that used a cyclical learning ring and cyclical momentum, pointing to different kind of ideal values for the learning rate, and the model will be cycling through these learning rates in a ascendant way until the middle of the training, and then done right again, which would help mainly with the subtle points in the mid part of the training, and then specifying down to the minimum local easier. He also proposed the use of learning rate test, which is a function that kind of simulates a training epoch with different kind of learning rates, as we can see down here. And they point out ideal value of the learning rate that could be used theoretically to have a lower loss or a higher accuracy, which is kind of useful to not guess with kind of the magic what kind of the best learning rate would be. On the result of this experiment, we trained with 3 different CNN model architectures, BG16, ResNet 34, and DenseNet 121. Each one was kind of an evolutionary step in order to see how the new models are, or the new architecture models are better in the training. And we use a FastAI library in the Kaggle kernels of the training. But quick about the model, BG16 is a mostly straightforward DCNN model. And ResNet is a model that introduced the residual learning blocks to deepen the training. And DenseNet took the base of the residual learning block and concatenated all the layers, creating a common feature map between a dense block with n layers, usually 8 or 16. As we can see, our metrics of accuracy and precision are over 99% in almost all cases, with it being progressively better with the more newer models. So we can see right now that the models can accurately predict plant disease detection in Plant Village. However, we have to point out that these are results taken in laboratory with laboratory images. As Florentinos and Barbero have tried previously, when we take these models, train it in the laboratory, and then we deploy them on the field with real crops, the accuracy steeply drops over to 40% and lower. So then we still have a knowledge gap between the laboratory and what we can see in the field. In conclusion, we can say that smart farming is a mature field. We have seen studies over the functionality of the security, error measure, error classification, and for me, especially interesting seeing the impact of rural farmers and social problems that can be can bring on this technology, and how can we solve them. Especially in our condition, we're seeing a high value of drones. As we saw, drones were being heavily used in almost all kinds of fields. In my opinion, the bird's eye view that they bring kind of closes the gap between a field image taken on the ground and a satellite image. It's still a really high level view of the field, but we can look closely to the details that are in the ground. It's mainly using photos, which is then again a curious thing. We know that machine learning and DCNNs can be used with another type of image, for example, sensor image or water condition image, for example. And then we also can see that disease detection is working great on lab images. Right now, in the future, as we can see, we can actually use machine learning to reduce water, waste and water pollution and kind of lower the stress and the heavy use we are exerting on the planet resources. And also we can see that in the future we have the possibility to create a disease detection system that can be easy to use across the world, that can be hosted in a server to being used. But until we close this gap between the laboratory conditions and the field conditions, we can't really use it in the real world. Our further investigation is just doing that. We are right now researching, for example, using segmentation to lower the amount of noise of a field image and using it with the model training in Plant Village. But still, the neck bottle here is the dataset. Until we don't have a comprehensive datasets of field condition of different kind of crops, we won't be able to create this kind of disease detection system that will be so useful across farmers around all the world. That will be for my presentation. Thank you for listening.
Okay, thank you very much, Bruno. Very good presentation. We have some question. Christian Aravena asked from a slide, the previous one, the 13, no, the 13.
13?
Sí.
The third one?
13.
13. Yes.
No, it's 12. Okay. We have similar question as these results include some kind of cross validation because the metric are very high.
Yes, this
and very similar.
This is also being done with cross validation in two datasets. We did not reserve a field dataset for test, but it has been done with cross validation. It is very similar. In fact, the photos that they had a mistake were usually the same kind of photos, mainly in tomatoes and maize that had kind of similar kind of photography. But we did do a cross-validation training, and we are confident there should be on the results of the project.
Bruno, this is the same. It's the same paper. Or there are different papers?
No, this is the same paper.
The same paper. Okay, and the disease is made in lab?
On cattle. No, not on cloud, on cattle.
But in lab?
No, yeah, they are lab photographies. As we can see here, let me see.
It's made in carrot in carrot.
No, in Kaggle. Kaggle
okay.
is an environment that is like a collab Google environment for machine learning training that lends GPU over for training.
Okay.
Around 66 before week.
Okay. The background is black. Okay. This is the paper or not? These are images from the same paper?
Yes.
Okay. It's very high, huh? Very high.
yeah, it's very high. But then again, there's the gap between this kind of photos that are black and the photos that we see in the field. So it's a deceiving high accuracy.
Okay. Did you find some work in disease but not in lab?
Doing this paper, no. Currently, we found out 2 datasets that are being used from Plant Pathology Challenge. They are Apple images exclusively, and we're kind of using them to find out a way that we can use this model training in Plant Village in order to have good results with those photographies that are taken in an orchard in, I don't remember the country exactly, but in an orchard in field conditions. That's
Okay.
the only other data set I found that use it and field images, however.
Can you back to slide 13?
There.
Okay. 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 Is when you yes, Christian Aravena is he say again, it's very high.
Yeah.
Yeah, but I think that the data is made in lab with a black background. Is okay. It's possible to obtain very high result. When you see that CNN are king and SVM are generalist, what do you think about that?
About, let me see, going back to the slide to
slide 8
here. Mainly I say this, King, as pointed out that they are being the most used model. In fact, I think if we add all the other kind of model being used, we still like only barely reach the amount of deep CNN being used in papers. When I say that SVMs are generalists, it's mainly because they can be used across various kind of problem. As we can see, CNNs are mainly being used on types of image, especially on field and aerial images, while SVMs are used across a more varied field. Also, we see this the same in kind of the problems being addressed. CNNs are mainly being used for geo prediction, disease detection, and Vitascope quality, while SVMs are again comparatively being used in a lot more of problems such as navigation, quality, segmentation. Those the labels, can you see the labels in the x-axis? Already being covered?
All this that you choice is based on image?
Yes, these are the 41 papers. Each point, each number is the amount of papers, and that uses kind of and all your other they are on images.
But they are based
they
are based on image recognition?
On image recognition, yes.
Okay. Okay. Very nice.
Thank you. Another question?
We having time? No, it's okay. Thank you very much, Bruno. Very good presentation. Felicitaciones.
Muchas gracias.
We have time. There is no more paper. I think that it's okay. In the program we finish. So thank you very much for your attention. I hope you're enjoying all the presentation from Silvana, Eric, Hugo, for two, and finally Bruno. Okay. Thank you very much, everyone. See you in EVIC tomorrow, starting EVIC. Okay, Escuela Verano de Inteligencia Computacional. Okay, so see you. Bye bye. Thank you very much.
Chao, chao, que estén bien.
Chao, Pablo.
Hola.
See you, Hugo.
Hola. Hola, ¿me escuchan?
¿Sí?
Hola, soy Rocío. Escucha, una pregunta. ¿Vamos a regresar a bueno, en unos minutos para el siguiente bloque?
Así es, así es.
Ok, gracias.
Sí, no hay problema. Esta sesión, este bloque ya terminó. El siguiente bloque comienza a las 4:30.
Ok, gracias.
No hay problema.
Es en el mismo enlace.
En el mismo enlace. Hola, Millaray.
Hola, hola. ¿Todo bien aquí? Recuerda que me
Sí.
tienen que enviar la información de las personas que presentaron, que no presentaron.
Y
Todos
presentaron
presentaron.
todo y sabes que al principio me preguntaron por las facturas. Así que no recuerdo quién era, creo que era Hugo.
Sí,
Eh,
creo que era Hugo.
Así que creo que lo mejor por el tiempo es que vayan a la sesión 8 porque está Nelson.
Sí, pero va a ser un poco difícil ahí que se hable de eso.
Oh, okay, cool. So again, I'm Nicolas Rojas Morales from Chile. I live in Viña del Mar, really near. Oh, no, not near. Really far from Temuco. But well, now we're in this online life. So I have to make some reminds to you. All the presentations should be in English, and questions should be made through the chat. At the end of the presentation, we have 15 minutes for each presentation and 5 minutes for questions. I will write to you on the chat when you have 5 minutes left and 1 minute left, and at the end I will send you a message when the time is over. So we have the first presentation of the article entitled Towards Explainable Artificial Intelligence for the Leukemia Subtype Recognition. Rocío Ochoa Montiel.
Yes.
I don't know if you can share your screen to see your presentation.
Okay. Do you see my screen?
Yes, please.
Okay. I don't know how. Well, can I start?
Yes, no problem.
Yes. Well, good evening, everybody. I am Rocío Ochoa. I am here to present towards explainable artificial intelligence for the leukemia subtype recognition. And this is joint work with Gustavo Lage and Humberto Sosa from the Computer Research Center in Mexico. They are my advisors. Well, now about motivation. Well, the visual analysis of medical images is an essential task to detect the changes in diverse tissues to diagnose some diseases. But what is the blood cancer or leukemia and how it is detected? Well, leukemia is a malignant progressive disease in which the bone marrow produces increased numbers of immature or abnormal leukocytes. Among the tests that exist for the detection of leukemia, a visual analysis is a complementary test for the detection of abnormalities in the cells. This test, however, is the best because it's cheap related with other tests that are very expensive and often are unavailable for people. Well, on the other hand, there are alarming data regarding the increase of leukemia cases, since only in the United States, there are more than 1 million new cases and more than 500,000 deaths this year. For this reason, we use in this work the evolutionary vision paradigm as a way of explainable learning to address the problem of leukemia image multi-class recognition. Yeah, well, for this, we propose that the image recognition problem will be introduced from the standpoint of data modeling. This means that we have an objective function to minimize, and the model that we use is based on genetic programming. For this reason, we have into the objective function variables like functions, terminals, and parameters used for tuning the algorithm. And also we have the data and the labels for each data. Well, additionally, we need, or we use, in this case, two elements. The first is a feature extraction method, named in this case artificial visual cortex, and other element named a brain programming. This is a suitable criterion C for minimization. These two elements are the most important parts of the proposal. So the algorithm for minimizing the criterion C, in this case, is a multi-layer perceptron. It's to note here that we can see another classifier. However, in this work, we use the multi-layer perceptron. Well, this classifier is in charge of learning a mapping, where the descriptors X are associated with each label J. Now, regarding images, well, in this work, we was in contact with a laboratory that allows to acquire the images. So for this reason, in this case, the data set is composed of 868 images for bone marrow smear color images from 4 subtypes of acute myeloid leukemia. These types are M2, M3, M4, and M5. Image acquisition is performed by employing an optical microscope with a magnification of 1,250 times and a camera coupled to the microscope. The image size is of 256 by 320 pixels. We have a balanced data set with 215 images per class in this case, and we show an example of each class of this leukemia. Well, for the experiments, we divide the images in 3 sets. We have the typical training set, the validation set, and the test set. In this case, we use the first 2 set, learning and validation set, for train the model brain programming, and the test set is used at the end to test the model. This is a difference regard other proposal. Now about the model. Well, in general, this is the sequence of elements that compose the model. So like in other, or in a classical genetic algorithm, we have an initial population, we have operators, evolutionary operators like selection, crossover, and mutation, and an evaluation of the objective function. So an important difference is that here we use other model into this that is named artificial visual cortex. The other elements are similar that for classical evolutionary algorithms. Another important thing is that the individual representation is a multi-tree. Is a structure with a multi-tree where we have one individual with a structure of four parts, and then well, this is the representation. This way, an individual consists of a set of functions and encoded in a multi-tree representation. So a variable number of syntactic trees ranging from 4 to 10 compose each individual. As a consequence, the model uses the individuals created for the recognition task. No, well, we have additionally functions and terminals for the evolutionary visual operators. In this case, we have two sets of operators of functions and terminals, because we have in this case an individual with a structure with 4 components. That's why we have in this part 4 types of functions and terminals. Okay, now the visual cortex, the artificial visual cortex. Well, this is a general scheme, and the ABC is a hierarchical model in which a representation of the object of interest is created from the image visual features. This representation consists of salient points in the image to generate a descriptor used for classification. The input of the ABC is an RGB image named iColor. So multiple color channels are considered to create the set color. This means that we extract from the image each band from the color space RGB, CMYK, HSV, where the elements will refer the color components of these color spaces. The orientation, color, and shape dimensions independently transform the input image iColor. This way, each visual operator is applied to generate a visual map for each dimension. Now, the next step is to compute a center surrounding process. The conspicuity map is an image that is the result of a set of transformation, is calculated as the difference between the different scales that are obtained through a pyramid of 9 levels. This is in the square with a line, with a line. And a Gaussian smoothing filter is used on each visual map to calculate each pyramid. This produces an image that is half the size of the input map. The process is repeated 8 times to obtain the 9-level pyramid. This is the first stage in this structure. Later, each level of the pyramid is normalized and scaled to the dimensionality of the visual map using polynomial interpolation. Finally, in the second stage, the 6 levels are combined into a single map with a summation operators. As a result, a conspicuity map is obtained for each dimension. The second stage on the ABC is description and classification. Here, a map named a mental map is built to highlighting the most salient feature from the conspicuity maps. These maps occupies the 4th position of the tree onward. So this is the LACCI image that we can see in the figure. And this element, this last image, is the 4th position and in the tree. Once the mental map are obtained and concatenated with the remainder of the syntactic tree, the generated program is applied to each image. And finally, the 200 Higgs values are used to define the descriptor vector for each image. So all this process is based or is inspired in a psychological theory and neurologics discoveries, and this is the motivation for this model, hierarchical. And well, finally, we work with the descriptor obtained through all these transformations. And well, regard the experiments, we use classical parameters for the algorithm. Generations, we use 13, population size, 13 individuals, initialization with the method ramp and half, crossover rate of 0.4, and mutation 0.1. Tree depth, it's a dynamic depth selection, and dynamic map depth with 50 levels, and a maximum length of gens of 10, and selection with roulette wheel. Analytics keep the best individuals. We do the implementation in MATLAB, and a PC with Windows. Then with results, well, when we trained the model, the best solution looks like this. An individual is formed with these components. In this case, we have the component of orientation in the first line, of color in the second, component of shape in the third line, and the last three, the mental maps, are the component generated for the best solution. According to the structure of the individual, we said that we could have until 10 gens, 10, but in this case, the solution has six components in this case. 3, because here we can see 6 lines that components out to the best solution. So on the other hand, we show here the results for the best solution in line 4, in the row number 4, where this was the Higger value for accuracy for the classification of 4 classes. And additionally, we use 2 classifiers to evaluate the model, an multi-layer perceptron and random forest. The behavior was similar with the test with the test set, and additionally, we have here that the class that is better recognized, excuse me, is the class M2. Yes, while the poor class for recognize is M3. This may be because this type of leukemia has well, many cells together. Maybe this is the reason. And additionally, here in the second graph, the indices of image corresponds to class M2. If we start from right to left, because here we show the descriptors. We have 200 descriptors obtained by the visual cortex. Yes, and the height of the lines here corresponds for each class of image of leukemia. Clearly, the descriptor values show the difference between the categories, which in some cases could be evaluated with simple techniques instead of using a classifier. For in this case, we use a classifier. And in the first graph, we show the fitness behavior of the best solution, where we can see that accuracy is increasing along the generation occurs. And finally, we use the depth and the number of nodes to quantify the complexity of the best individual. This figure illustrates the behavior of the number of nodes and depth of trees, which decreases as the generations progress. Thus, the final solution has low complexity in both cases. And to end, we address the problem of leukemia subtype recognition by using an evolutionary vision model. The evolved descriptors through the hierarchical structure and a functional composition are interpretable and can be simplified. Thus, we consider this model as a representative approach to explainable artificial intelligence. And the model can be useful in several areas, since the recognition problem requires a clear explanation to better understand the studied objects. And thank you for your attention.
Thank you very much, Rocio. I don't know if there any question. We have time for one question.
Yes.
Well, in the chat, there is no question. I have one question in slide number 11.
Okay.
I was wondering if did you used any parameter tuning algorithm to define these parameter values? There are a few ones, or how you try different values for the number of generations, population size, crossover rate.
How the question is how I determine these parameters?
Yes, correct.
Well, the training of this model, it's a very consumed time. And these parameters are obtained from the literature and classical parameters because we see that one execution may be your 200 hours, for example. And for this reason, we use parameters like these that are in literature, and we still not test another parameters for this. But this is the reason in literature we take this data and first, and when we test, we see that the time is very long for each run. The reason we take from literature these parameters.
Okay, perfect. Thank you very much, Rocio, for your work. Congratulations, and really interesting presentation.
Thank you.
So let's start with the next presentation. I have to present myself now. I cannot share the screen because Rocio still, okay, maybe I can now. Yes.
Thank you.
So can you see my screen, please?
Yes.
Somebody?
Yes.
Thank you very much. So, well, I'm going to introduce myself. I'm Nicolas Rojas. I'm going to present this work we made with Maria Cristina Riff, and it is entitled Reducing the Effort of Evolutionary Calibrator Using Opposite Information. So, well, this is the contents of my presentation. I first will introduce the parameter setting problem, some tuning algorithms that are in literature, and the motivation of our work. Then I'm going to speak about some related work about opposite learning strategies. Then I'm going to present our strategy named opposite scoring and how we evaluated this evolutionary calibrator tuner. Tuning to meta heuristics, and at the end I will speak some conclusions on future work. So we all probably know meta heuristics, and probably you know that meta heuristics require the definition of some parameter values previously to before to the execution of these algorithms. And also you may know that these values define in some way the performance of these algorithms. So let's see here this genetic algorithm. Previous to its execution, we have to decide some some parameters like which crossover operator will be used, which mutation operator, which selection procedure can be used. And also we have some numerical parameters like the crossover rate, the mutation rate, or the size of the population. Also, in some cases, we have different precisions for each parameter. So we have many possibilities. And we know this problem of selecting suitable parameter values as the parameter setting problem. It is a difficult problem, a combinatorial problem one. And it is difficult because of the stochastic nature of metaheuristics. The performance of these algorithms change through the parameter instances and also through different problems. It is a really unknown and not easy to understand relationship between these parameters. And if we try to define these parameter values, it is required to execute many times this algorithm. So it's necessary to consume a lot of time to obtain these suitable parameter values. Luckily, we have some strategies in literature that we can use to define parameter values in metaheuristics and in algorithms in general, like parameter control or parameter tuning. In the case of parameter control, there are some strategies that values are defined during the execution of algorithms, and these values change during the execution. And in the case of parameter tuning, we predefine these values, and they are fixed during the execution, and these values are obtained using different algorithms and that use different strategies also. So there are some very popular tuners like SMAC, ParaMyLS, Evoca, Iris, and Clois. And this figure tries to summarize very general how the tuners work. So when we want to tune an algorithm, we have to define which instances will be considered as the training ones, the parameters that we will tune, how we will measure the quality of these algorithms, for example, the quality of solutions or the number of evaluations consumed to find solutions, etc. The budget of resources. So the tuner will define this scenario and will try to evaluate several parameter configurations using a particular strategy. And the target metaheuristic will return the quality of using that particular parameter configuration. And the tuner will try to optimize the performance of this target metaheuristic. Okay, so tuners in general are focused on finding suitable parameter configurations for this test training set of instances. That means that these tuners usually maintain or use information about configurations that produce improvements in the performance of the target algorithm. And on the other hand, when the tuner found configurations that produce decrements in the performance of algorithms are usually discarded. And also the evaluations that the algorithm consumed and the information about this configuration is not used. Moreover, the convergence of these tuners can be compromised because they're usually almost learning about the promising configuration ones. And at the end, when you evaluate these configurations in the testing set of instances, the performance will be not necessarily the same that you obtain in the tuner. So we have this idea that what if tuners could be advised that some values were related to poor parameter configurations in order to obtain robust configurations when they will be evaluated in the testing set. And we know that there are some strategies in literature under the name of opposite learning that are related to learning about poor quality solutions for different kinds of problems. So opposite learning has been applied to improve the convergence of metaheuristics, the diversity of these algorithms, etc., among many other objectives. And it has been applied to solving continuous optimization problems under the name of opposition-based learning, and also combinatorial problems under the name of opposition-inspired learning. So there are several applications in many image heuristics, and in the case of the parameter setting problem, there are a few applications. For example, in parameter control, there are some strategies to define parameter values in the multi-objective differential evolution algorithm. Depending on the success of the algorithm, the parameter configurations are changed. And in the case of parameter tuning, we proposed this tuner in 2020 that use a tabu list that tries to store parameter values that were related to a decrement in the performance of the algorithm. So today, I'm going to present opposite scoring. Opposite scoring is a preprocessing step that learns about poor quality configurations. Why poor quality configurations? The idea is to force the tuner algorithm to explore configurations that would be originally discarded during the search process. As I said, most tuners, their strategy is related to only learn about promising configurations. So to force this exploration, we will inject a set of configurations as the initial set of configurations. And we propose to consume a percentage of resources, that is a hyperparameter of our strategy. And at the end of this preprocessing, we will obtain a set of configurations that will be used by the target tuning algorithm, and it will consume the rest of the resources. So our hypothesis is, if we spend some resources in learning about unpromising candidate values, tuners can obtain similar performance configurations using less resources, or in the best case, better ones using same budget or resources, the total resources. So what happens in opposite scoring? What is our strategy? During this preprocessing step, the algorithm will collect information about parameter values that were related to poor configurations. For this, we search in an opposite direction of the objective of the tuning process, using a hill climbing first worsening procedure, a very simple local search procedure. And the idea is to obtain an estimation of how promising can be this tuning process considering some particular parameter values. So during this preprocessing step, we compute a score per value metric for each parameter value possible for each parameter that considers the quality of the configuration of the value that participates in that configuration. It considers the number of evaluations for that particular value. So in summary, this metric gives priority to values that have the best possible performance during this preprocessing step, and also to give priority to values that were more evaluated during this first step. So at the end, we will have this score per value for each value, and a rank-based wheel selection mechanism will construct a set of configurations. So to evaluate our strategy, we select the well-known evolutionary calibrator that is a tuner algorithm based in an evolutionary algorithm. And we tune two algorithms, LACCI, that is an Ant-based algorithm that was proposed for solving multidimensional LACCI problem, and also a genetic algorithm proposed for solving the NK landscapes. We perform 5 independent executions for tuning each target algorithm. We considered a maximum budget of resources of 5,000 evaluations. And we experimentally define the percentage of resources that our strategy consumes. So we define that the 10% of the resources was the most suitable one for these two algorithms. These are the parameters that were tuned in the case of LACCI, these 3 ones, and this is the precision, and in the case of the genetic algorithm, these other 3 parameters. I don't have much time, but I will try to explain very generally the results and what we observed. So in the case of AdNaxApp, we first study the convergence of evoca when we inject this first set of configurations. And we see evoca and OS evoca. In the first portion of the evaluations, the EOS uses these evaluations to search in the opposite direction. And you can see that near to the half of the number of evaluations, evoca converges and don't produce better configurations. Then near to 3,000 evaluations, OS evoca reached similar quality configurations, and also in the last portion of the evaluations, it reaches better configurations. About the comparison, you can see the results in the article, but this table shows the gap to the best known solution for each of these instances. And we have the configuration of evoca and OS evoca. And in general, LACCI is allowed to reach better solutions with the configuration that OS evoca provided. And in the case of the genetic algorithm, the situation is quite similar. We have, in this case, a different quality measure, because we use number of evaluations used by the genetic algorithm to reach an optimal solution. And in this case, we consider 15 categories, each one with 1,000 instances. And when a result is in bold, one algorithm outperforms the other. So in general, using our strategy, evoca reached the better parameter configuration. So to conclude my presentation, I have 2 minutes left. Today I presented this initialization strategy named opposite scoring, that the idea is to learn about unpromising configurations, produce a set of the initial configurations for a target tuner, giving priority to the values that produce a better performance in the target algorithm. So we made this evaluation in evoca, tuning AdNaxApp and genetic algorithm, and we obtained these preliminary promising results. The main conclusion is that using these provided configurations in evoca, evoca reaches similar quality parameter configurations using fewer resources, and also we obtain better parameter configurations using the same amount of resources. And for future work, we are interested in evaluating this strategy in different tuners like IRES or a model-based one like SMAC. And also we are working in designing different opposite learning strategies to initialize tuner algorithms, forcing the exploration to probably spaces that the algorithms usually discard. So we have these references, and thank you for your attention. I don't know if there is any question. I'm on time. What is the influence on the population size in the performance of your proposal? In this case, well, we used this evoca algorithm that is actually an evolutionary algorithm. So we defined the number of configurations that we produced in our strategy, depending on the population size of the evolutionary calibrator. So it mostly depends of the hyperparameter of the target algorithm, because we will only produce the number of configurations that it will be necessary. So that's the only thing I can say about it, because it depends of the target algorithm. Thank you for your question, Rocio. I don't know if there is any more question. Well, I will explain a bit more about it. Going further in the question, if we increase the number of configurations required and we maintain the resources, we will see that less resources will be used for each parameter configuration at the end. So the higher the number the higher the amount of resources for our first step, the lower will be the performance of the target algorithm. So there is a balance between this budget of resources that we will study in the future work also. I don't know if there are more questions. If there's not, I will present the next presentation. I lost my. So we are on time to the third presentation. I will stop sharing my screen. The title is Modeling the Social Interactions in Gray Wolf Optimizer. Rodrigo Lira, I think is
I'm
here.
here. Can you hear me?
Yes, perfect. And you can start sharing your screen. Rodrigo, I'll going to Rodrigo, I'm going to tell you in the chat when you will have 5 minutes left and 1 minute left. I prefer don't speak to you during the presentation.
Okay.
Please.
Can I start?
Yes, start, no problem.
Okay. Hi everyone. My name is Rodrigo Lira, and I'm gonna to introduce our work modeling the social interactions in Gray Wolf Optimizer. The paper was developed together with Mariana Macedo and Ronaldo Menezes from University of Exeter, UK, Hugo Valadares, my co-advisor from Federal University of Technology, and my advisor, PhD advisor, Carmelo Bastos Filho from University of Pernambuco. This is our agenda, and I'll follow the section from our paper. So let's start. And the number of swarm-based algorithms has increased significantly in the last decade, based on different metaphors. Despite different inspirations, many proposals use similar mechanisms on operators. Therefore, it's relevant to have ways to assess the behavior in these algorithms to understand their similarities. Interaction network is a tool proposed to assess the communication dynamics in swarm-based algorithms that was already applied in different swarm-based algorithms as PSO, FSS, ABC, and CSO, for example. In this paper, we model the interaction network of Gray Wolf optimizing, and then we study the patterns that emerge from it in different scenarios. Let's take a look at the swarm algorithm. So in nature, gray wolves live in a pack, and they organize themselves in a strict social hierarchy of 4 layers. Alphas at the top are the most dominant and it leads the pack. Beta is the second layer and it reinforces the commands of the alpha. Delta are the scouts, sentinels, elders, caretaker. It is the third level. And the lowest level is omega. Also, the wolves hunt in a group and they follow a specific set of steps as we show here in this slide. Inspired by the mentioned behavior, Mijalili et al. Proposed Grey Wolf Optimizer GWO in 2014. In the proposal, each wolf represents a candidate solution, and the three test wolves are considered alpha, beta, and delta. In the movement, the entire swarm is influenced by them. In addition, the movement equations is modeled to reproduce the group hunt. We used the interaction network to assess the interactions between agents. It was proposed by Oliveira et al. In 2015, and in its core, IN, interaction network, is a graph where a node represents an agent and an edge represents the interaction between two agents. In our proposal, in order to narrowly analyze the GWO behavior, we changed the IN equation to use Euclidean distance as degree of influence among the agents. Our experimental setup used Rosenbrock and Hastings as benchmark function because each of them requires different balance of exploration and exploitation. And in each function, used 15 and 30 dimensions and 30 agents in both options. Also, we performed 30 simulations for each scenario with 1,000 iteration per simulation. Portrait divergence and Quebec divergence were used as metric to evaluate the networks. PD is a network size metric that evaluates the network structure, and KD evaluates the network flow. We show here what the values from both metrics means. When portrait divergence has values close to 0, it means that we have similar structure. When we have PD values close to 1, it means different structure. Quebec divergence, when it is close to 0, means similar flows, and close to 1, different flows. Let's see our results. The box plot here shows the fitness found by GWO on the third simulation for each function using all the setups. We see that using hashing, the GWO converged to the local minima, while using Rosenbrock, it reached the local minima and its surrounds. When we analyze the fitness values through iterations, we found that its convergence is fast in all the proposed scenarios. Now, here we are looking at the interaction network by iteration. We see that the influence will be much higher in the beginning of optimization. For example, in A, we see that iteration 1, the maximum value of influence between agents is 127, around 127. Close to the 100 iteration is the influence is very low, and the iteration 2000 iteration, 200 iteration is 0. Okay, what it means? It means that the leaders alpha, beta, and delta do not influence the swarm because it converges to the local minima. We see the same behavior in Rosenbrock, but there it reaches 0 with a high number of interactions. It should be noted 3 wolves influence all the swarms. Here, each iteration we can exchange the 3 fittest wolves. They are alpha, beta, and delta influencing the entire swarm. Here we show some snapshots of the cumulative interaction network with the fitness convergence. We see that for hash region functions using 30 dimensions, the swarm converged to in the iteration close to 90 here. The interaction network at iteration
Hello. I think we had some connection problems, or it's just me, please. Can somebody? Oh, okay. Rodrigo, are you there? Rodrigo? Hello. Can hear you, Rodrigo. Rodrigo.
Hello, can you hear me?
Yes, now we can
Ah,
hear
okay.
you.
Sorry.
Yes, we had some connection problems. You were talking about the convergence of the algorithm. We can start again from there. Yes, that was the
Oh,
slide.
thanks.
We will see.
Sorry.
No problem.
Okay, let's. I was talking about the convergence of algorithm. Yeah, here.
Yes.
It's some snapshot of the cumulative interaction network. We see that the algorithm using hashtree converged in 90 in the iteration 90 here, and the interaction network at the iteration 100 here and 200 here are very similar because the wolves are not influence each other. Okay, move on. And the current slide shows the final interaction network and its weight distribution. The weight distribution displays that there are hubs on the network because most of the links between wolves are close to the median value. That's more evident in hashtree, but Rosenbrock shows hubs in a smaller amount. Also, look here at the final interaction network, we see that GWO and GPSO have a similar partners. Okay, let's comparing the final interaction network over different simulation using PD and KD, we see that the final network structure does not change too much. Here, PD is smaller than 0.25. However, it varies the network flow. KD is higher than 0.5. Using 30 dimensions, we see the same behavior. And in addition, Marianne et al. Found a similar pattern in fish school search, investigating FSS. In our final investigation, we analyzed GWO using slide time windows of cumulative interaction network to see how IN involves. To do that, we create several cumulative interaction networks as we show here in the slide. So we create several networks and we compare it using PD, EKD. When you look at the network of the first 400 iterations, we observe that the cumulative network structure and the flow do not change entirely. It means that during the simulation, the network structure and the flow can change, but they maintain the main characteristic. So let's go now to the conclusion. We analyze the GWO social interactions using a framework called interaction network. We also investigate the partners over simulation and iteration using a new approach to create the network. Through IN, we saw that it's possible to identify the algorithm convergence because the leaders alpha, beta, and delta decrease or stop their influence in the entire swarm. And we found, seeing the final cumulative network, that some wolves act as a hub, sharing information with the swarm. We noticed that this pattern found in GWO is similar to the found by Oliveira et al. Using global particle swarm optimization. And using portrait divergence and Kubeck divergence, we found that GWO has a stable network structure, but not necessarily a stable network flow compared to the different simulation, as Mariana saw previously in FSS. So I finished my talk, say that the results show here the peculiarities of GWO interaction, but they also show the similarities among other algorithms. And it will be investigated as future work. And that's all. Thanks everyone for your time.
Thank you, Rodrigo, for your presentation. I don't know if there is one question in the chat. Someone has anyone? Questions? Well, we have plenty of time. So I have one question in slide number 12.
12.
I don't know if we can.
Let me see. I can see here the number. Yes. Okay, 12. Here.
12. Yes, yes. Well, I don't know if I correctly understand, but in the plots we can observe that in some cases, in the case of Rosenbrock, more than in Rastrigine, the same wolves participate in these alpha and beta layers. So if I'm not confused, maybe the thing that the same wolves participate in the influence of the other wolves can be a sign of stagnation of the algorithm, of if the algorithm has to explore more to change the solutions of the wolves, and also if you try different parameter values to observe how the exploration and exploitation is happening in the algorithm.
Okay. In the GWO only has one parameter that is A, and we follow the same value from the proposal that starts with 2 and decrease until 0. We not yet tested changing it, but we hope in the as future work investigate it more. Okay, but your first question was about stagnation. I
Yes.
don't understand.
Yes, in these plots, the idea is to observe that some wolves participate in the alpha and beta layers. The higher the participation, the higher the value of the red ones. Yes, I'm.
Okay, here is the final cumulative interaction network. We see that the wolf 1 influenced influenced more than 29. Can you see?
During the whole process.
Yeah, it's the final, summing all the interaction by iteration.
So that was my question. So if the same wolf was the one that mostly influenced the other wolves, this can be a sign of a stagnation of the algorithm. Why the other ones don't influence during the search process?
Okay, it's not the same.
Okay.
Each iteration, we can change the three test wolves, as we see here. In the iteration, at the iteration 1, it's 27, 1, and another here. At the iteration 100, we see that changed. So it will be changed every iteration.
Perfect.
Okay, it's dynamic.
Okay, thank you, Rodrigo. There are no more questions. Thank you very much.
Sorry for the problem with my internet.
No problem. It's the typical problems in this time. So great presentation. Thank you very much. The next presentation is entitled A Hierarchical Ensemble of LSTM-based autoencoders for Novelty Detection in Passive Sonar Systems. Victor Hugo da Silva?
Yes, I'm here.
Okay. Hello, Victor. You can start sharing your presentation. I can see your presentation, no problem. Congratulations, Rodrigo, says Carmelo. Okay, so you can start, Victor.
Okay. Good afternoon. My name is Victor Hugo. I'm a doctoral student of electrical engineering at the Federal University of Rio de Janeiro in Brazil, and I'll present the work entitled A Hierarchical Ensemble of LSTM-based autoencoders for novel detection in passive sonar systems. This work has been developed with Eduardo Sperg, who is an undergraduate student, and with our advisor, the Professor João Baptista. First, I will explain what passive sonar is and the problem within this context. Second, I will present the novel detection approach. After, I will show the database, followed by the results and the conclusion. Passive sonar is a detection system of threats in an aquatic environment. It comprises an arrangement of hydrophones and specific signal processing electronics dedicated to capturing the noise emitted from a possible target without emitting any signal. This captured information is processed and analyzed through its tonal and spectral characteristics. Here, as an example, we have two spectrograms referring to two different classes of vessels. We observe different vertical patterns that are related to the acoustic signature of each class. The sonar operator, who is a professional in this field, is responsible for identifying the acoustic signatures in these signals. His task is to predict if the signal comes from a known source or an unknown source. Unknown sources are also called a novelty, which may represent a threat. The use of automatic decision support systems will be very beneficial to the sonar operator. This system would help in his work by reducing the surveillance force required in this task. However, an ideal automatic system should contain information about all existing classes of vessels, but this would be unfeasible. Therefore, this system must be capable of doing novel detection. In other words, identifying unknown classes. This novel detection will be done by the novelty detectors. And how do they act? These detectors try to identify if test data belongs to some class of the signals previously exploited in system development. So, for instance, if I have a detector that has been developed with examples from classes A and B, and in the test phase I apply data from class A, it is expected that the system outputs a label non-class, but without specifying this class. Now, if I apply a test data from class C to the same detector, that is a class different from the ones used in the development of the system, then my output will be unknown class or a novelty. Basically, novel detection consists in two steps. First, from an input data X, we produce a dissimilarity score, S. Then we compare this measure to a threshold, lambda, contained in a decision block. If S is less than lambda, this is a low dissimilarity, so the signal will be considered as none. And if S is greater than or equal to lambda, the dissimilarity is high, and the signal will be treated as unknown or a novelty. This work proposes using a long short-term memory, or just LSTM, based autoencoders for the novel detection. Basically, the autoencoder is a neural network that encodes an input data under a representation of reduced dimensionality. So it uses the same representation to generate an output with the smallest possible reconstruction error. The LSTM-based autoencoder adopts an LSTM model along the layers of the network so that it makes possible to deal with the input data sequences and their dynamics. Here it is a LSTM-based autoencoder with a single layer. We consider that each spectral window produced by the passive sonar system is an ordered sequence. So each time step, T is related to a frequency bin of this spectral window. For the nova detection, the dissimilarity score is given by the squared reconstruction error. We will compare the results with two other techniques that has already been used in this problem. The first is the convolutional autoencoders. This network considers convolutional layers formed by convolutional filters. Like the LSTM-based autoencoders, for the nova detection, the dissimilarity score is equal to the square reconstruction error. The other technique used is the k-nearest neighbors that represents the current state of the art in this problem. Here, for the nova detection, the dissimilarity score is equal to the median value of the distance to the k-nearest neighbors. In this work, we investigated three architectures for the detector system. The first is called non-specialized, which is the most traditional. It consists of a system that contains only one detector. The second is the unanimous architecture. It is formed by a set of expert class detectors. That is, each detector is specialized in one of the known classes. In this architecture, an input data X feeds all the N novel detectors, and it will be a novelty if there is an unanimous agreement among all detectors. The last architecture is the hierarchical. Here, the input data firstly feeds a classifier block responsible for indicating the most probable class of origin of the signal indicated by the letter I. After only the detector I is activated and its respective output defines the final decision variable, D. To evaluate the system skills in recognizing a no event, first we computed the ith non-class detection rates, namely the KRI. So for each non-class I, we sum all detection hits. In other words, if a non-event is predicted as a non-event, then we divide it by the total elements of the class. Next, we computed the global measure, AKR, that is the average non-class detection rate. It is equal to the arithmetic mean of the KRI values, assuming the existence of n known classes. Now, if you want to evaluate the capability of the system in novel detection, we have to present to the system events that belong to different classes than those used in training. That is, events of unknown classes. So from the database, we reserve a set with some classes to perform this task. So similarly to the previous slides, we have to compute the ith unknown class detection rate, namely the URI. It is equal to the average of detection hits of events that belong to an unknown class. With these values, we'll obtain the global measure, AUR, which is the average unknown class detection rate. It is equal to the arithmetic mean of the URI values, assuming the existence of R unknown classes. The choice of threshold lambda present in the system will define these rates. So we can draw a commitment curve for these rates, AKR and AUR. The area under the curve, named AUC, indicates the system performance. So the higher the AUC value, the more effective will be the system. Brazilian Navy Research Institute provided a database. It contains audio radiated by 28 ships belonging to 8 different classes, namely the A, B, C, D, E, F, G, H. The signals were acquired by a single earphone situated on the Brazilian Neve acoustic range seabed, located in Rio de Janeiro, Brazil. These signals were sampled, preprocessed, and normalized, generating about 30,000 spectral windows of 557 points, covering the range of frequencies of interest from 0 to 3 kilohertz. So from this database containing 80 classes, we needed to divide it into two sets, one with known classes for generating the system, and another set containing the unknown classes that will not be presented to the system during training, being only used in the test phase. We consider 3 evaluation scenarios, assuming 3, 5, and 7 known classes, which represent scenarios of different complexities regarding to novel detection. The choice of known classes for each case, we considered combinations of classes identified as the most critical. So for the data set, we applied a k-fold cross-validation resampling technique with k equal to 10. So we reserved 10% of the data for the test set, and we divided the remaining data considering 10% for validation and 90% for training. So at the end, we obtained the 10 triplets of trend, validation, and test sets. It's important to say that for each complexity scenario, we ignore data of unknown classes from the training and validation sets. Here, the highest AUC value in the validation set define the best hyperparameters. Now the results. First, for the 3 known classes scenario, here we have a graphic showing on the horizontal axis the different combinations of techniques and architectures, k-nearest neighbors with hierarchical architecture, convolutional autoencoders with hierarchical architecture, and the LSTM-based autoencoders with non-specialized, unanimous, and hierarchical architecture. On the vertical axis, the AUC values in the test set for the 10 experiments. We can observe that the hierarchical LAE has the highest AUC median value at about 0.95. And it's interesting to note that the results in this scenario are in the range of 0.93 to 0.96. For the case with 5 known classes, we note that the AUC decreased with the increase of the number of classes. They are now in the range of 0.9 to 0.95. Again, we observe that the hierarchical LAE stands out, presenting the highest median value of the AUC at about 0.94. When considering a more complex scenario with 7 known classes, we observe that the AUC values decreased even more. Here, the AUC is now in the range of 0.82 to 0.92. We can conclude that the increase in the number of known classes led to a reduction in the system performance in terms of novel detection. And again, the hierarchical LAE presents the highest median value of the AUC. Concluding, this work evaluated LSTM-based autoencoders in 3 different novel detection architectures for dealing with passive sonar signals. The proposed hierarchical LAE has achieved higher performance than the standard LAE technique, yielding to more efficient detectors than the state of the art. And for the future works, we can explore variation autoencoders and Siamese neural networks for this task. Well, this was the presentation. Thanks for your attention.
Thank you very much, Victor Hugo. We have time for questions. There is anyone that have any question? Please write it in the chat. Well, I have a few ones. I don't see the number of the of the slide, but the title of this one was database. I imagine that is like 3 or 4 slides back. Well, no problem. And the next one, you said that you used 90% of the data for training and 10% for the validation. I was wondering if you try a different proportion of this percentage in order to compare different scenarios to the state-of-the-art algorithms.
No, for this case, when I'm using the LSM autoencoders, no, we fix that this proportional 90% for training and 10% for validation. Remember that we reserved previously 10% of the original database for the test.
Okay. Okay, and I was wondering, you are comparing these unanimous and hierarchical architectures. What about the execution time of these algorithms? Did you evaluate or compare these architectures in I don't know, the resources consumed by the algorithms or the execution time? Do you have any idea of the difference in that aspect
between unanimous and hierarchical?
Yes, when you use these algorithms.
In unanimous, it's necessary to pass the data for all the novel detectors. Instead, in the hierarchical architecture, we choose one of the detectors and pass the data. So I think the hierarchical is more fast.
Okay. Okay. And I have one more question, but I didn't. Oh, there is. So you speak in some point of your presentation that you use some strategy to reduce the number of the dimensionality in some place of your presentation that you use
the number of dimensionality.
Yes,
I mentioned it during the explanation of autoencoders.
Yes, yes. So did you use this strategy in your did you evaluate how much this reduction is produced in your experiments, like to see if there is I don't know, like a proportion of the variables that are not considered at the end?
No.
Okay. Okay. Well, I don't have more questions, and we don't have more questions in the chat. Thank you very much, Victor Hugo, for your presentation. Really interesting topic. We will go now to the last presentation of the session. That is entitled Comparison of Feature Extraction Methods for Brazilian Legal Documents Clustering. Joao Lima is here.
I'm here.
I think. Okay. Please, Joao, you can start sharing your screen.
Okay. Can you see my screen?
Yes, I can see it.
Okay.
So you can start now if you want.
Okay. Hello. Good night. My name is João Pedro, and I'm going to present the article named Comparison of Feature Extraction Methods for Brazilian Legal Document Clustering, with authorship of myself, Dr. José Alfredo Costa, and Diógenes Carlos Araújo, all from the University of Rio Grande do Norte, here in Brazil. So first, we're going to make a brief introduction on the context where this paper was produced. And according to the Justice in Numbers report, Justice in Numbers report,
of National Justice Council, the Brazilian National Court Council, Brazil reached a number of 77 million lawsuits in 2019. But approximately 84% of these lawsuits were created in the PJE platform, which is an online platform used by the most Brazilian courts of justice. So this is the ideal scenario for apply artificial intelligence models, as we have a large amount of data, and this data is already available in a completely virtual way. So the objective of our work was to help the development of these models, focusing on the models for clustering legal documents. And clustering itself can be described as the process of finding natural groups in our data set, and it can be very important to the legal domain, as it can be applied to tasks such as mass trial, data organization, and data exploring. Here we can see the usual form of a model for document clustering. We have a feature extraction algorithm, which is responsible for turning texts into numbers, followed by a dimensionality reduction algorithm, and finally by the clustering algorithm itself. And our research focused on empirically evaluating different feature extraction algorithms to decide which one is the best. So here are a few algorithms that we evaluate, and we try to answer this question. So a little justification of our research is that the clustering of legal documents, is a special category of problem, because first you have the vectorization problem, that texts are difficult to represent numerically, and choosing an algorithm to perform this task can be difficult. Second, we also have the problem of legal text itself, which have their own structure and vocabulary, and it makes it difficult to use pre-trained models and generic databases. And last but not least, we have the legal ethical needs for applying artificial intelligence models. They need to be interpretable, transparent, and auditable, so we can ensure fair and unbiased judgments. So in our research, we tested 6 different models: binary bag of words, TF-IDF, word2vec pre-trained, word2vec trained on our base, and doc2vec. I'm gonna make a little summary of each one of them. First, we have one of the simplest language models we can have, which is binary bag of words. And it encodes the document as a vector, uses zeros and ones to indicate the presence or the absence of a specific word. It's a Boolean vectorization algorithm. Following, we have the bag of words, which is a more common form of algorithm. It encodes the document using the frequency of each word in the document, very similar to the binary bag of words. The TF-IDF vectorization algorithm is one of the world's famous algorithms, used in a lot of places and researches, and it encodes the algorithm using the TF, the word frequency in the document, the TF part, as well the word frequency in the corpus, in all the documents. It's the IDF part, the inverse document frequency. Following, we have these 2 word2vec models. Basically, they are the same model that embeds words into dense representations using context-aware neural networks, with the difference in how they are trained. The first one is a set of pre-trained vectors in Portuguese texts from NILC repository, and the second one is a set of vectors trained from scratch in our own database. And finally, we also use the doc2vec model, also trained in our database. So the experiments were conducted on a database of 30,000 legal documents made available by the Tribunal de Justiça do Rio Grande do Norte. This is our local justice court. And this base is divided into 10 original classes, 30,000 each, 3,000 each, sorry, and which we use to evaluate the performance of the clustering algorithms. So this table demonstrates how the experiments were conducted. To access the performance of the algorithms, they all work on the same pre-processed test, this block over here, this white block. And for each one of the models, we tested different dimensions. We tested 50, 100, 300, 600, and 1,000. And for the first models, binary bag of words, bag of words, and TF-IDF, we also tested two different versions. One counting only for unigrams and other counting for unigrams and bigrams as well. And as word-to-vec models only embeds words, we consider the document vector as the average of the word vectors. And we have the doctor vector model. It's not being changed. The cluster algorithm chosen its K-means because it's fast and simple. It's quite used over there and popular. The algorithms are tested over two different sets of cluster numbers. We have this first set over here and the second set over here. This first aims to simulate the situation where the number of clusters, the number of clusters is unknown, and the second where the number of clusters is known, which in our case is the original number of classes, which is 10. The results are evaluated using the NMI and RI score, which stands for Normalized Mutual Information at Random Index, using the original classes as the grounded truth. So moving on to the results. First, let's analyze the results in the simulation of the unknown clusters. That's a lot of information, but we can summarize a few important points. First of all, these two graphs, these two first graphs, shows how the scores vary over the number of clusters. This one of the left is the normalized mutual information, and this one on the right is the random index. In the x-axis, we can see the number of clusters in log scale. And we can see that TF-IDF is winning by a good margin over all the other models in both scores, in NMI and in RI. And this is not a surprising fact, given the nature of our data set and the way TF-IDF vectors work. Second, binary bag of words has a surprising performance. You can see this blue line over here. Even being one of the simplest models, it was able to reach high scores, being in second place many times in both scores also. We cannot distinguish well the performance of the two word-to-vec models by looking only at these two graphs. You can see that the performance is very close in both graphs. And the performance of doc2vec was very bad, also in both scores. So another important point to note is that TF-IDF is the only model that has a well-defined point, a well-defined peak over here in the number of clusters 8, here and here. And this can easily help us to define an adequate number of clusters. So looking at the distribution of the overall scores, these two graphs over here, and we can see that TF-IDF has the high values in both scores. The distribution of TF-IDF is very high in both scores. And the second place seems to be to the word2vec trained on our base, this last over here and this last over here. But it's very close to the word2vec pre-trained. It's a little higher, but it's very close to the word2vec pre-trained. And from these two plots, we can also see that the performance of the bag of words models is pretty inconsistent here and here, less inconsistent, but also inconsistent. And it can vary from very high over the word2vec models and very low, below the Doc2Vec models. And on the other hand, the performance of the Doc2Vec is consistent, but it's always low in both scores. So following, we're gonna see the results when the number of clusters is known, which, as I mentioned before, it's 10. So this first table shows the model's overall statistics. Again, you can see that TF-IDF is the best model in every score, and is followed by Word2Vec trained on our data, Word2Vec pre-trained, bag of words model, binary bag of words, and lastly by Doc2Vec, which has the worst performance. In fact, if you can see, the worst scores of the TF-IDF are one of the highest scores in all the table. So the TF-IDF is a very good model. In comparison with the previous results, none of the models seems to be beneficiated by the equality between the number of clusters and the number of classes. The scores don't grow if we already know the original number of clusters. And we also access the model's qualities over different dimensions, these two tables over here, and both scores seems to grow with the number of dimensions, with many of the highest ones centered in the highest dimension. These last columns here, in both tables, we have the highest scores. So another important point that we have to evaluate when dealing with machine learning in the legal environment, it's the interpretability, that it's our ability to understand and explain the decisions made by the algorithms. And ideally, we try to avoid black box algorithms and opt for algorithms that can be audited and explained. And in this aspect, it's preferable to use traditional methods like binary bag of words, TF-IDF, this one on the left, and which are based on simple rules and produce vectors with easily interpretable. So moving on to the conclusions, the TF-IDF model was the best in every aspect of this research. It reached high scores, and its implementation is simple and it favors the application in the legal domain. Both Word2Vec models reached similar scores, but its implementation uses deep neural networks, which can be a problem if the model needs to be audited or interpretable. On the other hand, bag of words model have the best implementations for legal domain, very simple and transparent, but they are inconsistent and often low scores. And Doc2Vec has the worst performance in every aspect because it not only has low scores, but it also based on deep neural networks, and it's not suitable for the legal domain application. So that's it. We want to thank the supporters of this work. They are shown on the screen, and also the conference for the opportunity. Thank you.
Thank you, Joao, Pedro, for the presentation. Congratulations for your work. We have one question. We have time enough for one question. Joao Baptista says, considering the Word2Vec approaches, how do you aggregate the multiple word embeddings produced to each document?
Okay. I'm trying to, okay. As I mentioned in this slide, as I assume that you're talking about how I take the words vectors and turn them into a document vector. And this okay. Yes, I just do the mean vector. I take all the vectors and do the mean vector of all the words that compose the document. It's a very simple strategy.
Okay, thanks, says Joao Baptista. So thank you very much, Joao, for your presentation. This was the last presentation of the session number 7 of Evolutionary Swarm Computation, Neural and Learning Systems. Thank you very much for attend the session. And
Thank you.
see you in the next activities of the conference. Goodbye. Thank you to Rocio, Rodrigo, Victor Hugo, and Joao for your presentations. And hopefully we see each other in next years. Bye.